Hi, my name is Jeremy Lopez, and I am the lead for the gas turbine experiment. A quick outline of what we do, and jump right into it with an introduction. You can see this is an example of a jet turbine, and I mean there's the fins in the back, and the nozzle is going to be air is going to be going in, and it's going to be undergoing Brayton cycle, and to where the thrust. Or the air is going to be expelled at the end at really high speeds to produce thrust. The objective of this experiment is to understand the Brayton cycle and how the principles of the gas turbine, also to record temperatures and pressures and thrust over a range of values for RPM, and also to calculate the performance of various components of the turbine. A little background here is the Brayton cycle. From 1 to 2, you have isentropic compression in the compressor. 2 to 3, there's isobaric, which is constant pressure, combustion. 3 to 4 is isentropic expansion in the turbine. 4 to 5 is isentropic in the nozzle, expansion of the nozzle. And this actually, that's the ideal case. And you can see the dashed line is the real case, which, because entropy is not going to be constant, and you're going to have a little bit of change in there. And also you can see at the bottom it doesn't really connect. It's because it's not a full cycle, because it's not using the same fluid over again. It's having new air go in. Here's a model of the turbine we'll be using. There's a bunch of readouts for different temperatures and pressures. And you can see sort of where the compressor is and where the nozzle and turbine is inside. Now, the efficiency of the jet engine is calculated by the ratio of the thrust per unit fuel consumed, and also as the ratio of the pressures increases, which the pressure ratio is the compressor exit pressure and the ambient pressure. And as that increases, the efficiency increases, which as efficiency increases, you're going to have higher pressures, higher temperatures, and that means higher stresses acting on the material, so you need better material to actually make to where it's sustained at those high temperatures, because it is going to be high stress situations. Procedure, you're going to be operating, and there's a list of procedures on the wall above it. You don't want to do it without a technician, and follow safety guidelines for this one in particular. Use earplugs, so it's going to be loud. And you're going to record the load cell reading and different pressure, temperature, fuel mass, flow rate, and thrust data in different increments from 40,000 to 80,000, and then take 5 readings at arbitrary speeds. There's a bunch of calculations in this lab, and they're all in the lab manual, so I'm not going to talk about them fully, but see, it starts out with the first law of thermodynamics. You're able to calculate a bunch of things involving temperature and pressures. And so there's more. You're given the density of the jet fuel, and you're giving the energy released by the jet fuel combustion, and a few other equations: fraction energy, thrust. You have the fraction fuel burned, and here you can calculate the work of the turbine and the compressor. A little bit of analysis. We're given some data points in the lab manual and what to expect, and here's a plot of the fuel flow versus RPM, fuel flow versus millivolts, the fuel meter. And you can see they're very similar diagrams. They don't change much, although the fuel flow versus RPM is slightly closer to the linear fit than the other one. And so I would say that one would be a better choice just because it's more consistent answers. And now for the exhaust velocity, you can calculate using air mass flow rates. You can calculate with stagnation gauge pressure, and also with thrust. We're actually in the lab manual. We're not given the data like the thrust and the pressure data to calculate what the velocity is, but you'd use these equations to do so. I tried finding data online for the thrust and pressure, but because we're not given the exact thrust and pressures for this model, we don't know exactly what, it's not going to correlate, and my answers didn't really figure that out. Yeah. Sort of already said how the pressure ratio is related to the efficiency, and because as the pressure ratio increases, so does the ratio of the thrust, therefore as the pressure increases, so does the thrust. And any questions?